on to the next speaker. Next speaker is on site, Wondo Rhee, first-time presenter, so extra applause for that, please. And if you like the talk, he's also looking for job opportunities as a recommendation system engineer, so he's here. Reach out to him. And today he will be talking about countering popularity bias by regularizing score differences. The floor is yours.
Oh, thank you. Hello, my name is Wondo Rhee from Seoul National University, South Korea. And the title of my presentation is Countering Popularity Bias by Regularizing Score Differences. And before I begin, I'm really happy and excited to present and participate in my favorite conference, and I hope everybody enjoys my presentation. All right. So recommendation systems are used in various domains. The RS learns user preference from the data and recommends items. Meanwhile, the popularity bias is a phenomenon that can come in many forms. At the one hand, the data shows long-tail item distribution. At the other hand, the RS model trained on such data often over-recommends popular items than the data warrants. So even if the user equally likes two items, the popular item is recommended more because it is ranked or scored higher by the recommendation system model. And that is what we refer to as model bias. So the model bias is a problem that can harm personalized recommendation, and it must be solved. So our study focused on solving model bias. To solve this, we propose to minimize the score differences of positive and negative items, respectively. In my presentation, I will demonstrate how model bias can occur. I will introduce my debias method and compare with earlier debias methods and show and report empirical experiment results. So starting with the preliminary, in implicit recommendation system, the training data consists of user, item, and their interaction information. The recommendation system learns positive and negative preferences from the data and computes recommendation score. Often, such implicit RS is trained with the Bayesian pairwise ranking loss. Using the BPR loss, the model pairs positive and negative items of each user and learns to score positive items higher than the negative items. Next, we demonstrate model bias and how it can occur. We train the RS model on biased synthetic data. We design a 200 by 200 user item interaction data where the item popularity is linearly skewed. So the figure on the right shows the synthetic data in matrix form. The row corresponds to user and the column corresponds to item. And the white triangle shows the items the user consumed. And we can see the item popularity decreases as item index increases. So the item index 0 is consumed by everybody, and as the index increases, the popularity decreases. So training a recommendation system model on this data, we get the model score prediction in the figure below. And we can observe a salient model bias because the popular items, which is items with smaller index, scores higher than other positive items. So even if we condition on the positive items, like where the white triangle is, we see the scores of items of the left side, the popular items, is higher, like 10, than other positive items on the right side, which has a smaller score. To measure the accuracy and model bias more concretely, to compute accuracy, we compute it by taking the average, the positive items scores higher than the negative items for each user. And the measured accuracy was very high with low error rate of 0.01%. Next, to measure model bias, we measure whether the top scoring positive items of each user are also the most popular positive item of that user. So the figure on the bottom right shows the popularity quantiles of the top scoring positive items of each users. The quantiles are focused on 0, which means highest popularity. So the graph shows the top scoring positive items of each user is also the most popular positive item of that user. And we averaged this 200 popularity quantile to get value of 0.02, which shows high model bias. If there were no model bias, the popularity quantile will be spread across 0 to 1, and the average will be close to 0.5. So now we know that the model bias can occur. We want to solve it. To achieve this, we propose a method of using a regularization term to minimize the score differences of positive and negative items respectively, to be used in addition to the BPR loss. We propose the zero-sum term. So during training, positive and negative item is sampled, and the sum of their item score is regularized to be close to 0. This would lead the positive and negative item scores to have symmetric value. And as the regularization propagates through random positive and negative item pairs, all positive items, hopefully, the scores of the positive items will converge to a single value, and the negative item scores will converge to a symmetric value. And since positive item scores converge to a single value, this would minimize the score differences of positive items and reduces model bias. So we extend the BPR loss to include the zero-sum term. The BPR loss trains to achieve high accuracy by contrasting positive and negative items, and the zero-sum term trains for high debias performance. And since the two computations are orthogonal, these two objectives can be simultaneously achieved. Next. So let's test this with the synthetic data. The figure on the top right shows the model score prediction results when training with the BPR loss and the zero-sum term. So we immediately see drastic reduction in model bias because the positive item scores are now more smooth horizontally for each user. And at the same time, the model still clearly contrasts positive and negative item scores, thus maintains high accuracy. The graph below now shows the popularity of the top scoring positive items is now spread across different popularity, also indicating low model bias. The table shows the accuracy when using the proposed method does not decreases, but even slightly increases. So our method showed a bias reduction as well as high accuracy. So that was pretty nice. And we next compare our method with earlier debias methods. We group some earlier debias methods as the score adjustment debias methods. These methods tries to adjust model score by lowering the scores of popular items and boosting those of unpopular items by training weight adjustment or score post-processing by popularity and such. But often these schemes are heuristically designed, and in our experiments, we saw the method does not generalize to other RS model when using a different recommendation system model for training. However, the logic of the zero-sum method is more intuitive, and we observed it to be model agnostic. Next, some earlier studies tried to regulate the Pearson correlation of item scores and item popularity for positive items to achieve debias, so that the item score and popularity is independent. This is a similar idea to the zero-sum method, but the downside of the correlation regularization method is that the Pearson correlation takes too much computation, because all the positive item scores needs to be computed for one step of training. In contrast, the zero-sum allows mini-batch training and requires minimal additional computation. Finally, the quantitative results shows the zero-sum method outperformed earlier methods when testing on the synthetic data. And finally, we conduct empirical experiments. We use 4 benchmark datasets and 4 RS models and compare the proposed method with 5 debias methods with the BPR loss as the baseline. We have evaluated both accuracy and debias metric with relevant metrics such as hit and DCG and the pop Q, which was implicitly explained earlier. We noted, however, that most debias methods showed accuracy loss as a result of the debias process. Therefore, we had to decide what would be considered good performance, since we are taking into account 2 metrics that didn't always go hand in hand. We argued that high accuracy must precede the debias performance because low model bias but with low accuracy is just random accurate recommendation and not personalized recommendation. So we finally decided accuracy loss at most 2% of the hit from the baseline with at least 0.07 value increase in the pop Q to be good performance. So this is the result for the movie lens dataset. There are 4 big columns corresponding to the 4 recommendation system model used. The rows show the debias method with the zero-sum method in the bottom and the baseline, the BPR loss, at the top. The cell shows the results with the good performances emphasized in bold. We see the zero-sum method showed good performance on all 4 RS model. So that is, compared to the baseline BPR loss at the top, it showed a minimal, small accuracy loss and an increase at the POP-Q, so high modal bias reduction. For other debias methods, this was not always the case. The PD and Pearson method showed good performance with the matrix factorization, but not so much on the other models. Now we see the results for other datasets. The zero-sum method showed good performance with the second and third dataset, but not so much on the fourth dataset. But other methods showed even less consistent result than the zero-sum method. So the zero-sum method showed more consistent good performance than other debias methods. With this fact and the additional computational advantages discussed earlier, we conclude the zero-sum method generally improves over earlier debias methods. And this slide summarizes the presentation. We propose a method to solve the popularity bias, especially modal bias. We used a regularization term that minimizes the score differences of positive and negative items respectively. And the method has several advantages, and experiments showed it generally improved over earlier debias methods. And more information can be found in the paper. And that is my presentation. Thank you.
Thank you. We have lots of questions, and we can't address all of them, but some are really upvoted a lot. So the first one is, how do you disentangle 2 types of popularity bias? Quality of contents versus limited content exposure arising from the bias in the data.
So what I noticed was that the term popularity bias is used in many different ways in the literature. And I touched on it briefly in the first slide, but I distinguished data bias, and data bias could be affected by the exposure or the skewed popularity of the users. But I tried to distinguish that and not solve that, but only solve the modal bias, bias in the model prediction. So I think the lots of forms of popularity bias needs to be formed separately, and I only tackled on one particular part of it.
Okay, thanks for clarifying that. Then another upvoted question is, how are the negative items selected for a positive item?
How is it positive? How is it selected?
How are they selected, yeah.
Just randomly.
Just randomly.
Yeah.
That was a quick answer on a long question. Then did you also try out other loss functions, and like how does it, like did you consider that, or how did you select the way you've done that?
So in our paper, we actually compared another regularization term, and also it is not in our paper, but we figured that the method, the idea or the goal was really close to like a pointwise loss, having the exact same value for each prediction. We tried to experiment with the pointwise loss, but I recall that it didn't really show much difference. And since the sampling methods integrated more naturally with the BPR loss, we went with the BPR loss as the baseline loss. And more information about additional regularization term is included in the paper, so refer to it, please.
Okay, thank you. Referring to the paper is always a good option, because you should all read it. So thanks a lot.
Thank you.
Thank you. There are a lot of more questions, and they will all be transferred to our platform afterwards, to the hub. So please go there for more questions and answering. And I'm ready to transitioning to the next speaker. I'm really happy to welcome you here on stage. It's Ki-Wan Meng. Want to mention he just took a position as a first-year assistant professor at Penn State, but now today is presenting work that is done at Meta. And the title of today's work is toward fair federated recommendation learning, characterizing the interdependence of system and data heterogeneity. The floor is yours.
Hey, thanks for the wonderful introduction. I am Kiwan Meng. So this is, like she said, the work that I have done while I was at Meta. So start right away. So the clock is not moving. Is this? There's the countdown clock. Maybe I can go on. Anyways, so brief 1 minute introduction on what I'm going to talk about today. So recent studies increasingly, it's working. Recent studies increasingly started to look into training a recommendation model using federated learning to enhance user privacy. When training a model using federated learning, prior work extensively studied the effect of data heterogeneity and system heterogeneity. However, they failed to look into any potential correlation between the two, simply assuming that the two heterogeneity are independent of each other. In this work, we aim to study if such an assumption is true, and if not, what can be a potential effect, especially in terms of fairness. So this is going to be the overview of the rest of my talk. First, I'm going to talk a little bit about the motivation and the background, and then I will talk about the two data and system heterogeneity and a potential correlation between the two. Then I will talk about our simulator, which can simulate realistic system-induced data heterogeneity, which is the correlation between the two heterogeneity. Then I will show you some evaluation results and conclude my talk. So a little bit more about the background. To train a recommendation model without having to collect raw user data, people have started looking into federated learning. To train a model in federated learning, instead of collecting raw user data, on each round, the server selects a subset of the client to participate and sends the model that needs to be trained to each client. Each client then train their model on their local device using their local data. And when the training is done, they send back the model to the server where it gets aggregated and one global server-side model is calculated. And this process repeats until the model converges. When doing federated learning, there are two types of heterogeneity that can complicate the training process. The first is called data heterogeneity, which refers to the fact that different clients may have different data distribution. For example, some clients may like apples more, while some other clients may like bananas more. And depending on their fruit preferences, of course, the recommendation system will have to recommend different items to the user. There's also something called system heterogeneity, which refers to the fact that some clients may have low-end devices with limited computation and communication capabilities, while some other clients have higher-end devices which has more computation or communication capability. This imbalance in system capability cause low-end devices to become the bottleneck of the entire training process. So some prior works proposed tier-aware optimizations that essentially applies a more aggressive optimizations to lower-end devices to balance the overall computation or communication time between different tier devices. Some of the popular tier-aware optimizations, for example, are shown here. Google's smart keyboard's next word prediction model simply disallows low-end devices from participating in the training process entirely. This is a very radical form of tier-aware optimization. Some other works, instead of entirely excluding low-end devices, often proposed running a degraded computation or communication on low-end devices. For example, they pruned or quantized the gradient more severely on lower-end devices to reduce the communication cost, or they used less channels or smaller models on low-end devices to reduce the computation time. So that was the brief background. And these optimizations that I just talked about were all shown to be very effective in prior works. However, they had one big assumptions in common about data and system heterogeneity when they were testing out these optimizations. That is, when simulating data and system heterogeneity, what prior work essentially did was they first started from a dataset with data heterogeneity, and then they randomly assigned to each client a synthesized or collected system heterogeneity statistics. For example, they just randomly assigned like this client has high-end devices, let's assume this client has low-end devices, and evaluate the result. By doing so, they are essentially assuming that data heterogeneity and system heterogeneity has no correlation. In other words, the probability of liking an apple or bananas are essentially the same regardless of the device tier the user has. In such a synthetic scenario, even if you apply a tier-aware optimization to low-end devices, it does not really introduce any fairness problems because high-end devices and low-end devices essentially have the same data distributions anyways. However, you can think of a hypothetical case where low-end devices tend to like apples more for some reason, while higher-end device users like bananas more for some reason. In such a hypothetical scenario, you can see that data heterogeneity and system heterogeneity are tightly correlated with each other, and we say that the dataset has high system-induced data heterogeneity to refer to such phenomenon. So what does the real-world data look like? Due to the interest of time, I will not show you real-world data statistics. It is in our paper. But by analyzing real-world data from production recommendation models, what we found was that real-world data indeed has a high system-induced data heterogeneity. Data heterogeneity and system heterogeneity are tightly correlated, just like the example we saw, instead of what prior work assumed. And you can easily imagine that when there is such a high system-induced data heterogeneity, if we apply a tier-aware optimizations, for example, if you simply disallow low-end devices from participating, what will happen is that the end model would not work very well on low-end devices, which is mostly Apple lovers, because the model is highly biased towards high-end devices, which is mainly banana lovers. Again, is this effect real? With production data, we saw that this fairness effects can happen in real-world data. We applied popular tier-aware optimizations to our real-world data and saw up to 16.7 times more accuracy degradation on lower-end devices compared to higher-end devices. Again, this kind of fairness problem was not observed or reported in any of the prior work to the best of our knowledge, because prior work during their evaluation assumed the data heterogeneity and system heterogeneity did not have any correlation. So how can you study these kinds of effects when you don't have access to real-world data like us? That is why we designed RF², which is a simulator that can simulate realistic system-induced data heterogeneity using open-source datasets. RF² first takes a popular open-source recommendation dataset, such as Taobao Ads Click Display dataset or Movie Lens dataset, and it synthesizes different levels of system-induced data heterogeneity on top of the open-source datasets. It particularly uses Dirichlet distribution to control each device tier's affinity to different items. What I mean by that is that it can make some device tiers like apples more, while some other device tiers like bananas more, just like in our earlier example. And there is a parameter alpha, and by tuning the parameter, we can make the system-induced data heterogeneity really high, as we saw in our production example, or we can also make it very low, and that will be similar to what prior work assumed. With the synthesized system-induced data heterogeneity, RF² supports training popular recommendation models using federated learning, such as DLRM or DIN, and using popular tier-aware optimizations. And finally, it can estimate the resulting accuracy and fairness. For more details about our system, please again refer to our paper. And now let's look at some interesting results. So we evaluated RF² with 2 different open source datasets, 2 different models, 6 different levels of system-induced data heterogeneity, and 6 different tier-aware optimizations. The tier-aware optimizations that we studied can be, are shown here. We studied excluding low-end devices, which was the approach Google Smart Keyboard was using. We also overselected the clients by 20% and dropped the 20% slowest clients. We also tried using different gradient pruning based on the device tiers, different gradient quantization based on the device tiers. We looked at 2 different gradient quantization methods. And finally, we also looked at using different channel size depending on the client's device. For the fairness metric, we used maximum difference in accuracy change. So I will gonna only show you a subset of the result because of the interest of time. So here I'm showing the result when we exclude low-end devices from training. And there are 6 bars. Each bar shows the different level of system-induced data heterogeneity. From the left, no system-induced data heterogeneity as what was assumed in the prior work. All the way to the right is very high system-induced data heterogeneity. And the y-axis is the fairness metric, which is higher means more unfair. What you can immediately see from the bars is that even if it's the same optimizations, depending on the level of the system-induced data heterogeneity the data set has, the fairness implication can be very different. We saw up to 15.8 times fairness difference in this particular example, and for some other cases, we've seen up to 41 times fairness difference. So this implies that if you assume no system-induced data heterogeneity in your evaluation, just like what prior work did, you can mispredict the real fairness impact. You can downplay the fairness impact by up to 16 to 41 times. We now also show the results from other optimizations as well. So here, what you can see by comparing different groups of bars is that these are all similar optimizations with similar overhead, but you can see from the height of the bars that the fairness implication can vary significantly between different optimizations. Again, this effect can be only seen if you assume a realistic system-induced data heterogeneity in your simulation. Otherwise, these interesting effects is not really visible. So here you can see that gradient pruning is more unfair, and even between gradient quantizations, depending on exactly what quantization method you are using, some are more fair than the others. Finally, we also saw that best accuracy optimization is not necessarily the best in fairness. So if you compare these two groups of bars, the first bar at the end showed better average accuracy, but the second group of bar was much more fair, as you can see from the height of the bars. This implies that it is very essential to study fairness as well as accuracy when you're studying federated learning and different optimizations, especially in, again, realistic system-induced data heterogeneity dataset. You can see more characterizations and results in our paper. And this is my final slide. I will just conclude my talk. So we have seen that system-induced data heterogeneity exists in the real world. It is very real, and it can cause real fairness impacts. So RF square is a simulator for you to study those kind of effects when you don't have access to real-world data. And our evaluation shows that RF square can simulate such a realistic effect, and you can have interesting observations about your optimizations that you are designing. This is the end of my talk. Thank you, and I will be happy to answer any questions.
Thank you. A lot of questions are flowing in. Let's start with this one. Are we implying correlation or causation between data system-induced heterogeneity? Data and system-induced heterogeneity?
So I guess the question is whether it is more like a correlation or causation. So that is what we don't know for sure because we haven't analyzed the real-world data to that extent. But what we tried to do was whether it is actually a causation or correlation. We wanted to simulate similar effect on open source data set with what we were observing from production data.
Okay. Does improving system accuracy for low-end devices decrease system accuracy for high-end devices, or is there a way to balance potential accuracy trade-offs?
So that's a really good question. So this paper is more about characterization and introducing the simulator. So it can happen where improving low-end devices accuracy can, sometimes it can degrade high-end devices accuracy. And whether that's a good thing or not, it depends on your system's goal. But we believe that this framework can promote future researchers to study those kind of effects and possible solutions.
Okay. Then there's an interesting one. I find it interesting. What is the fairness definition here? Less powerful devices do less computation and contribute less due to resource constraints seems fair by intuition?
Mm-hmm. Yeah, so it's, again, a really great question. So the metric we used was simply whether the accuracy degradation after applying the optimization is similar between devices or not. And because low-end devices do less computation or communication, maybe people can think it is fair to just make them have worse accuracy. But again, I think it depends on the goal of your particular system.
Okay.
Is there like a physical?
Ah, sorry. Question? Yes, one more question, and you're here.
Thanks, interesting talk. So I want to understand, is the basic thing here that your evaluation set on what you're evaluating is very different from the production, deployment? So essentially, you're saying that because your evaluation isn't the same, your performance will degrade, right? Because I couldn't think as the system as one confounder. There could be other confounders that if you don't have in your evaluation, you will have these kind of problems in production.
So sorry, can you repeat the question?
Yeah, what I'm trying to say is, so you're saying because of this system heterogeneity, your performance would degrade, right, in these lower systems. So let's say the system is one kind of confounder. You could have other such problems because of which your performance would degrade in a subset of recommendations. So what I'm saying is the essential problem that your evaluation is, where you're evaluating that population is distributed differently from your production population?
Sorry, I don't think I understand the question correctly.
I'll
Can
check
we
with you later.
take it offline?
Yeah, maybe that's a good idea to chat after the session on that.
Okay.
So thank you
Thank you.
again for your presentation. Our next speaker joined